Hi, this is Koiro with the fifth installment on the Plus 4 series. And this is the fault that happened last time that we saw. We had this dollar sign down here on the screen. And it actually was a dollar sign. And if you tried to enter some other characters in the same place, you saw that it was shifting and showing other characters than what you typed on the keyboard. And this is a subset of the Petsky characters that's commonly used on most of the Commodore machines, at least the 8-bit ones, and they all have a subset of this, and not every one of these is equal amongst the machines, but the main ones are the same along the whole line. Now I see I actually have a fault here. I forgot the letter E and have twice entered D, but that doesn't matter in this analysis. And what we saw last time was that the space was giving us a dollar sign. And we also saw that the 0 was giving us a 4, and that a 9 was giving us a equal sign. We saw that the A was giving us a E. It actually did matter anyway. And a K was giving us a O, and a P was giving us a T, and that an X was giving us a pound sign. And if we analyze what the difference between a space and a dollar sign is, we can see the answer here in the third bit. And as we can see, the difference between a space and a dollar sign is that this bit is 1 on a dollar sign and 0 on a space. And if we analyze this bit further down here, we can see that that is actually the difference of all of these character that's shifted. So we can conclude that the third bit, or bit 2 as it's called since we start on 0, is actually causing this fault, and it seems like this bit is stuck on 1 and will show a 1 in each case. To show this more in the big picture, I've actually pictured it here for those who is not very familiar with how the bits is organized inside a 8-bit computer. And we can see here it's bit 0, 1 and bit 2 that is affecting us. And the question we have to ask ourselves is what's causing this? And I think the first thing I would do is to isolate the memory address that's faulty, and it could be more addresses. That is just that we are looking at the screen memory that shows this just here. It could be all the faults, other parts of the memory, but it's not displayed here or is affecting the functionality of the computer. So the question is, what memory location is this? And to answer that, we have to look into the memory map of the Plus 4 computer. And the Plus 4 computer has the video matrix for text starting at hexadecimal 0C00. And if we type that out on the Plus 4, we will see that the location for this character is F2D, or 3885 in decimal. And if we take a look at the schematics of the Plus 4, we actually get some help. And the simmers.net website is a very good source for schematics and other stuff regarding several Commodore computers. And this is not the original schematics from Commodore. It's actually something that was displayed in the Hungarian magazine back in the 80s. I think this is a more clean layout of the schematics, and it shows all the major stuff that's on the main board and all the electronics that affect the running of the computer is displayed here. And also displayed from Commodore is that you have some troubleshooting guide for the Plus 4. I had a video earlier where I went through some of the material for troubleshooting a Commodore 64, and this is actually the same for a Plus 4 computer, but the Plus 4 computer is far less detailed and there is far less common situation and stuff because it was a later area machine, and it also had a lighter spread than the Commodore 64, so it actually was fewer sources to get good documentation. They say they should check for the U1 for proper operation, and the U1 is the TED chip. And we can rule that out, I think, and if the TED chip is broken, the computer is very much toast in itself, because that will not be something that's easy repairable, as you have to gut another C16 or plus 4 to get a new TED chip. The next you can check is the CPU, and we actually just changed this CPU from a Commodore 16 machine, and the Commodore 16 machine did not have this fault on the screen, so I think we also can rule out that the CPU is the fault. And then they actually ask us to check the RAM data lines for correct amplitude and so on. And if there is something else on the data bus that is pulling one of those lines down, you will actually see that it has another signal level than a high and low. Maybe you can see that it's not closing 0 or closing 5 volt, but you can see that it's a bit between maybe 2 volt and 3 volt. That's in the illegal area for a TTL level signal. And then you can use that to conclude that it's something that's pulling the data bus low or high, and that the driver voltages and currents on something on the bus is not strong enough to pull it high or low. They also say that we should check the multiplexers, but the multiplexers actually affect the address lines. And if all the addresses was the source of this error, we should think that every one of the memory bits should have the same fault, and that would not just affect one bit if this was the error. And the ROM chip could of course be sources for error if they was pulling just one bit low. But as we saw, the computer is actually booting and running into both the built-in programs and other stuff. So I do think that the at least the kernel ROM is okay, but the character set ROM could actually be a cause of this, even though it's a less likely candidate. And they also state that we should replace all these chips with known good ones, and this is the PLA. The PLA on the Plus 4 is not the same configuration as on Commodore 64, but it do have the same mechanism for replacing and faults and so on. So this could actually be a step to replace this with good ones to check if this fault does occur. And I have all these chips socketed on my Plus 4, so I think it will be possible to change these to check if there is something wrong. And of course, they also say that bad basic random characters on screen could be caused just by the U23 chip, but that's already covered in step G and H, so I don't think that's the fault here. And if we analyze this a bit further down to the schematics, we saw that it was bit 2, and bit 2 is here stated. This is D0, D1 and D2. So it's U13 that is the culprit if it is a memory chip that is faulty. And U13 is placed so on the board, and it's quite easy to desolder this on Plus 4. Back in the day, we just cut all the pins here with a sharp cutter, and then we just desoldered each leg. And in some cases we didn't even bother to take out the PCB when we did this, because we was just removing the pins from this side. We placed in a new CPU and we was just solder it from the top, as all the holes are through platted on this. But I will take this out and I will save this chip, because it's an interesting fault with a RAM chip, and I probably will want to do some debugging on this chip later when we come as far as that. So let's now move into the shed and see what's wrong with this computer. To Today I'm back in the shed to do some more testing on the Plus 4. We have already established that this dollar sign down here is a problem, and we do think that this is a memory error if we look at the diagnosis of this problem. And I'm going to try to do some pokes here to see if we can get this character to change. Actually it was 3885, and we can try with the space sign, that's 32, and it didn't change. And then we can take 33, which should be the exclamation mark if everything is working, and that's in line with our theory. And I can also take and try to poke the address beside this one, and this will give us the exclamation mark. So we are pretty sure that our diagnosis is right, that it is the third bit, or not bit 0 and 1, it's bit 2 on the memory. And I'm going to desolder that chip, and I'm going to replace it with a socket so that we can put in this memory chip or another to just test it. I'm going to desolder the memory chip, but before I do that I need to take out the main board. You can see this connector for this keyboard is getting tired of being pulled out all the time. And I connected my body strap to the anti-static source, so it's the same potential as this. I don't always use a wrist strap. I use one of the body straps that goes around the waist. I think that's easiest. The memory chip that was bad, and that's U13. That's the right chip to desolder. And U13 on this is this one. That's U13. And translated to that, it's this one. And as I still haven't found my desoldering gun, I'm going to use this solder braid. And this is the good stuff with the built-in rosin. And at this point it actually started raining so hard that the sound from my camera was totally useless. The most important thing to remember when you use desoldering wick, beside from using a kind with a good amount of flux or rosin in it, is to keep the stubs so short that you don't have to use too much heat. And that's also true, you can't overheat each pad either, so move it to the next pad if you can't suck up more. And as you will see, I also use a trick where I do desoldering from both sides on these boards where you have true plated holes for the components. Back in school we learned that using solder bed was much easier on the solder pads and also on the components, as you would require less heat and that you also didn't have the extreme suction that you have of a suction pump. But this is actually a mixed experience, because sometimes when the solder blade doesn't suck too good, you have to use more heat. And as we see here, we do have some pads where I have to apply some more solder and take a second turn with the solder braid. And after you have done a manual inspection and seen that all the holes are open, even then it's wise to use a hot air soldering iron or a hot air gun with a thin nozzle to heat up the back of the PCB when you pull out the chip, to avoid applying any mechanical force on the solder pads. And this time all the preparations and hard work paid off. The chip easily come loose without persuasion. So now I just clean away the excess rosin with isopropanol. Yes, when everything now is cleaned up, it's about placing the sockets and soldering that in. And my way of doing that is that I pull in the sockets and I bend 2 or 4 of the legs to keep this in contact with the PCB when you do the soldering. Many of you use gum or some other fancy issues to do this. You can also support the socket from behind so that you keep some weight on it, but I think this works quite okay. And here I do kind of an experiment. I have used digital zoom in the editing software to zoom in on the soldering itself. So it's interesting to see how the quality of this looks when I'm finished rendering the video. And I'm washing all the soldering off with the isopropanol, as this is solder with a lot of rosin in it. It's very important to clean off the debris afterwards. Yeah, and now it's just about testing with a new chip. The chip that was in this computer was actually a 200 nanosecond chip, while the Shematics stated 150 nanoseconds. My replacement chip now from Samsung is 120 nanoseconds, and that might be a bit fast if the timing is tight. I do have some other slower chips if need be. Yeah, now it's just about putting it enough back together to make a good testing of this, and we need to attach the keyboard. You have to be careful with this connector, this is getting a bit brittle. But after this is just connecting power and video, and we are good to make a final test. I have now lined up the camera on the TV, and I'm trying to turn on the Plus 4. And there you go. 60671 bytes free. I have to check that number. But if we try to poke like this, we get the exclamation mark on the right place. And if I try to read it back, maybe it's not peak on basic 3.5. I thought it was. And here I actually made a complete fool out of myself. Of course the poke is working because that's a direct command to the computer. But actually to make a peak, we have to tell the computer what to do with the peak. And you can put the peak inside a variable, or you can use the print statement and just have it printed on the screen. So a peak in itself, of course, should give a syntax error. But the machine now seems to be working okay, so all our troubleshooting and detailed approach to finding the fault actually led to a quick result. So that's it for the series about the Plus 4. I hope you enjoyed the contents, and please subscribe if you want to be notified when we post new videos. Thank you for watching. See you in the next one.